Welcome to this overview of the first diffusion practical. So in this practical, we'll really walk through the complete diffusion pipeline. So we'll start from the raw unpreprocessed diffusion data, and then we'll use TopUp and Eddy to correct for the distortions and to align all of our diffusion weighted images. And then we'll use DTIFit to fit the diffusion tensor model in every voxel for our diffusion weighted images. And finally, we'll use TbsS to compare the anisotropy of these diffusion tensors between 6 different subjects. So this pipeline is illustrated here, but before running the pipeline, let's actually have a look at the diffusion data. So let's go to this directory. And if we look in this directory, the main file that we're interested in is this DWI data, which contains the diffusion weighted data, which I've opened up already. So this is basically what the first volume will look like. And to understand this first volume, we have to look at this bvals and bvax file. So the bvals file, let's have a look at what's in that. This is just a text file, so we can look at it with cat. And basically it contains one number for every volume, which tells us what is the B value for that volume. So how sensitive are we to the diffusion? The first one has a B value of 0, so we're not sensitive to diffusion at all. So this is our reference, our B0 image. If we go to this third image, we see that that one has a B value of 500. And so we expect a reduced signal because now we have signal loss due to the diffusion. And the higher the B value, the lower the signal. So as we move to the next volume, we have a higher B value, so even less signal. And then we move back to a lower B value again and a higher one again. And you can see that this amount of signal within the image is modulated by this B value. In addition to the B value, we also have the bvax, which define the orientation of the gradient. So this is the direction in which we're sensitive to diffusion. And this has 3 rows, and each row gives us the diffusion gradient orientation in one orientation. So the first is the X direction, the second is the Y direction, and the third is the Z direction, and contains one number for every volume. To see the effect of these gradient orientations, it's easier to look at a data set where we only have data with a single B value. So that's also included in this directory as the B1500. So this only has all the images which has that B value. And if we then start a movie, you can see the variability in between the different gradient orientations. You can see that there's a lot of signal variability in the white matter, because for some gradient orientations, the gradient aligns with the fiber orientation and you have a lot of signal loss. In other cases, it's perpendicular to the fiber orientation and you don't have as much signal loss. So the first part of the practical will really be exploring and trying to fully understand this data set. And if you don't, please ask questions. It is important for understanding the rest of today's and tomorrow's practical. Once we've looked at this data, we'll start looking at how we can pre-process this data. So in particular, what we will be trying to correct for here is this bright rim here at the top, which is due to the susceptibility-induced distortions, and the variability due to motion and eddy-induced distortions between the different diffusion-weighted volumes. So that's what the next part of this practical is. First we'll look at running TopUp, and then we'll be looking at running Eddy. Now, TopUp and Eddy themselves are so slow that we will not be able to run them within the practical. But we will be able to basically do all the steps that are necessary before running TopUp and Eddy to get the data into the right format. Now, something that's a bit different from the other practicals is that we don't actually give you the command to run this directly. Instead, we describe what needs to be done, and then we ask you to come up with the command on yourself. If you can't come up with it, of course, you can just press the reveal command and see what we would have done. One thing to keep in mind that makes it easier to come up with the right command is that if in FSL, if you type the name of one of these FSL tools without any additional flags, such in this case TopUp, and you press enter, what you will get is basically a usage description describing all of the inputs that this tool expects. So that makes it a lot easier to figure out what is the exact command that you need to get the output that you want. After running TopUp and Eddy, we should have a nicely aligned distortion-free diffusion MRI data onto which we can then fit the diffusion tensor model, and so that is where this tool DTIFit comes in. And here we describe 3 different ways to run DTIFit, but irrespective of which one you actually use, you always get the same output, which will look something like this. So basically here we can see that in every voxel we've estimated the best fit diffusion tensor. So in the ventricles where we have CSF, we see that these tensors are very large, indicating a large diffusion, while in the white matter we see very anisotropic diffusion. Most of the time you will not be analyzing these tensors themselves, but instead be analyzing some summary measures such as the FA, which quantifies how anisotropic are these diffusion tensors, or the MD, which quantifies how large are these diffusion tensors, or the V1, which is basically what is the preferred direction of diffusion, so this aligns with the long axis of the diffusion tensors. So after looking at this diffusion tensor output and hopefully understanding it, we can then move on to actually comparing these fractional anisotropies, so the anisotropy of the diffusion tensors between different subjects. So in this case, we've already provided you with the FA maps for 6 different subjects. So these are in the TbsS directory. So these 6 files are all FA images for 3 young and 3 old subjects. And the question is, how does the FA change between the young and old subjects? So mostly TbsS is just running 4 different commands, which are helpfully labeled TbsS 1, 2, 3, and 4. The only somewhat tricky one is running the first one, because here you have to give it all of the individual FA images. So in this case, because they're all in the same directory, it's quite easy. We can just use I should spell TbsS correctly. We can just use the star to select all of the nifty images, which are in this case all the 6 images that we want. In your case, it might be a bit more complicated to collect all of the FA images across all of the different directories you use to pre-process the data. But in any case, once you've run the first step, you can then, of course, look at the output from the first step and then run this subsequent step. And so basically, this goes through all the steps that were described in the lecture for TbsS. So first, it's registered to some type of standard space, and then in that standard space, we define the skeleton of the FA image, and then we project individual subjects' FA data onto the skeleton. At the end of this, the main output that will be of interest is the all FA skeletonized, which basically looks something like this. So so we only have values on the white matter skeleton, and on this white matter skeleton we basically have 1 FA value for every individual subject. And so if, for example, we look at the time series, we can see how the FA changes across the subjects. And then once we have this, we can run basically the same we can just run a GLM on it, as was described in the second and third functional MRI practicals. So in this case, we'll set it up using the GLM tools, and then we'll fit this GLM using randomize. So the output will basically tell us where is the FA different in the old population versus the young. So if we open that, let's close the time series so you can see it a bit better. You can see these voxels where the randomize was able to find a significant difference between the old and the young population. So that's basically the whole practical. So enjoy going through it, and please ask questions if anything comes up.